So thank you for coming to our OCHEM exam review today. Online, I should be unmuted now. If they can't hear anything, let me know, Frank. But this is the OCHEM 2 exam 1 review. So all of y'all will have spectroscopy on your exam, and I believe alcohol reactions. So we'll be covering those today. In the past, we've done these exam reviews virtually. We've used like PowerPoint presentations. So I thought we could do it a bit differently this year. One thing I'm going to be doing is I'm going to be mostly writing out notes as I go that y'all can follow along with. But I really wanted to sort of show everyone how I sort of studied for the class, while also going over the main points of, you know, IR, mass spec, NMR, and those reactions that we all know, right? So if you have any questions, feel free to ask them. I'm always happy to answer them. Just raise your hand. And online people, we have one of our tutors, Frank, here. He'll be answering questions virtually. So put those in the chat. Okay, let's get started. And if anything's like not clear or not showing up right, just shout it out to me. People in the back, can y'all hear me? Okay, good. Okay, so getting started, we're going to start with spectroscopy. We're going to take a short break, and then we'll go into alcohol reactions, and our last bit we'll be doing a bit of the problem set that y'all received in the email for this event today. But yeah, let's get started. This is the edge of the paper. Okay, so this is our OCHEM 2 exam 1. So I'll just write that out because that reminds me what I'm doing too. But let's see. So the first part of what y'all will be doing on this exam is spectroscopy. So one of the first ones that you might have learned is IR. That stands for infrared spectroscopy, right? And infrared spectroscopy is used to look at the bond vibrations of different bond stretches, right? So you're going to be looking at whether something is vibrating at a high frequency or a low frequency. The basic trends being that you have, you're going to be looking at both how resonance might affect the bond frequency, for example, and that also leads into the other thing, actually, sorry, you will be looking at bond order. So a couple things affect bond frequency. The first being bond order. So you're going to be looking at double bonds versus triple bonds versus single bonds. Triple bonds tend to vibrate at a higher frequency than second double bonds and so on. Second, you'll be looking at resonance because resonance affects that bond order. As you see something resonate, actually, it'll decrease the overall bond order of the bonds involved in the resonance structure. And finally, you also will be considered things like ring strain, which is simply if you have a ring that looks like this, which is just like a 4-membered ring or a 3-membered ring, God forbid, those are incredibly unstable. They're going to have a very high energy, bond frequency. So anything with high energy will be on the left, right? And your low energy bond structures will be on the right side. So you might remember from the trends that you saw that you have carboxylic acids are high energy, alcohols are high energy, your triple bonds tend to be high energy, your double bonds tend to be high energy, and on the low energy side, you tend to see benzenes, which have a lot of resonance. Even though they're a ring, that resonance takes over. You're also going to see carbonyl stretches, which are pretty high energy, but not as much as these sp2 and sp3, or no, sp and sp2 carbon hydrogen bonds. And hopefully that's moved up. Yes. Okay. But general information, how those trends go. But what y'all really should be focusing on is that there's different domains that we're considering as we read an IR spectroscopy. So primarily there's about, I would like to say like 4 different regions that you're going to be looking at when you look at an IR. So when you look, let's see, this should move down. When you look at an IR, the bar is on the right side. Don't ask me why, but we typically start reading our IR at 1600. So we're going to start there. So at 1600, before this is the fingerprint rate region. We don't really care about it. But past that, we start seeing at 1600, you expect benzene rings, right? So that's your first domain. If you're going to be looking at 1600 to see if there are peaks that relate to benzene rings, at the 1700 range, you're going to be, actually let's put 1700 closer, you're going to be looking for a carbonyl peak. So that is a double bond between an oxygen and carbon. So that can be either your esters, your ketones, your aldehydes, your amides, right? And some other factors will influence those. We can also talk about the order with carbonyls in a second. But so currently you have 1600, 1700. Your next region that you want to look at, and we're going to skip ahead, is at 2200. Below 2200, you have your C triple bond carbons, so carbon triple bonds. Above 2200, you have your carbon nitrogen triple bonds, so cyanide and C triple bond C. And one thing that you'll notice is that cyanide actually has a higher bond order, higher bond energy than your carbon triple bond carbon, because actually there is almost carbon and nitrogen are not equally electronegative, right? So there's actually a bit of a disjoint. How the electrons are being shared is not even. So you're going to see a higher bond energy. So that's your 2200. The next level that you're going to be looking at is 3000. So at the 3000 range, you're going to be seeing both your sp2 and sp3 carbons, sp2 and sp3 carbon hydrogen bonds. So sp3 is business as usual. That just means that you have single bonds. sp2 is the more interesting one. You can be looking out for that when you're trying to confirm, for example, benzene peaks that you see at 1600. You can go check if there's an alkene using that. So that's really neat. And then the last one, and what I consider the most fun, is you can be looking between the 3000 and 3500 range for either, and we're just going to use a bar here for this part, carboxylic acids or alcohols. So that's the overall domains that we're looking at, right? So we have 1600 for benzene, 1700 for carbonyls, 2200 for those triple bonds, 3000 if you want to differentiate, find those double bonds, and 3500 for carboxylic acid and alcohols. You'll also find amines right here. Right. So how do we differentiate? Let's start with actually what we just talked about with the carboxylic acids and the alcohols. There's 3 distinct peaks that you're going to be looking for. One of them is, let's see if we can push down. We're going to first look at alcohols versus carboxylic acids, which I'm just going to write as COOH. So alcohols tend to have a broad peak between, oh my, see if we can push up, between 3000 and 3500. So you're going to see that they center at the 3300 point, and they have something that looks like this. So it's a big peak that goes down pretty far, right? Carboxylic acids are also a broad peak, but they're also wider. Broad refers to the fact that this is just big across, it's not pointy, but carboxylic acid peaks will go out actually from 2500 to the 3500 range. So forgive the scale of this chart, it's not accurate, but the big thing that you want to know is that alcohol peaks are less wide than carboxylic acid peaks, which go between 2500 and 3500, which will look something like this. So they tend to be a little more pointy at the bottom. And then the final peak that you're sort of worried about around the 3000 to 3500 range is your amide peak and amine peak. This is just the bond between nitrogen and hydrogen. So you're going to be seeing those around 3400. And you'll either see 1 or 2 bonds. Those don't tend to dip down as far, but just look out for those peaks. If you have 2 peaks, that means you have a primary amine, which is just 2 nitrogen and hydrogen bonds, right? So be looking out for that as well. when we look at the carboxylic acid peaks, we will be considering, not carboxylic acid peaks, but these are the three for that 3,000 range. But let's also talk about carbonyls. We said that carbonyls are located around the 1700 point, right? At 1700, we're not going to see a very big difference. Y'all have learned probably about esters, aldehydes, and ketones at that peak, as well as maybe amides. And the order being that you're going to typically see that these are shifted further left. Yes? Oh, is it not shown? Okay, yes. Perfect. Yeah. Yeah, I can use the mic. Thanks for letting me know. Okay, so we're going to be looking at carbonyls. Is there anything that we might have missed that anyone wanted me to reiterate or answer a question about? Yeah?
For amines,
if
there's like secondary than primary, there's a difference in the way it looks up on IR, right?
Yes, so secondary and primary amines, the difference is going to be the number of peaks you see at 3400 range. So you're going to see 2 peaks for a primary amine, and what that indicates is that there's 2 bonds between nitrogen and hydrogens. So that means there's 2 hydrogens on that amine, right? And a secondary amine will only have 1 bond to hydrogen, so that will be 1 peak. So you can really count that as the number of hydrogens for those peaks. Any other questions? Okay, yeah?
When you find a peak that's just above 3,000.
Above 3,000? Mm-hmm.
Does the sp2, does that indicate that there's an alkene?
Yeah, so if you look at a peak right above 3,000, typically it will be like almost like a camel hump next to the peak right below 3,000 for sp3. That can indicate an alkene. So I think that's a really good way to confirm alkenes. Typically, you'll also see that from like the degrees of unsaturation, which we'll go over as well. But yeah, great questions. But yeah, so we were also talking about carbonyls. These are all found around the 1700 range, right? But there's minor differences. Esters tend to be your highest energy carbonyls. Those tend to be around 1735. Your ketones, no, you're not your ketones, your aldehydes tend to be around 1720, ketones around 1710, and amides around 1660. Now, you don't need to know these numbers by heart. When you're looking at that peak, it's just going to look like it's at 1700. But the reason it's important to recognize that difference is because sometimes you're going to be asked ranking questions. So it's important to notice that there is a difference, even like in bonding frequency between these carbonyl peaks. Specifically, something else to note is that the reason your amide peak is so much lower is because of resonance. So resonance causes a shift to the right side. So resonance shifts this right. So far so good? Oh yeah?
When we see the oxygen carbon double bond, we also see the NH stretch in the other side of the to indicate that's what it is.
So typically if you're going to see an amide, we've had a brilliant point. You're also going to be looking for a peak at that 3400 point, just like we talked about earlier. So there's typically other ways to confirm. This is mostly just to point out how that bond order works. But yeah, great question. And then our one differentiating factor between our carbonyls, which many of y'all might have heard about, is the one difference we can find is aldehydes. We can differentiate aldehydes from all of our other carbonyls, specifically by looking for fangs. Has everyone heard about the fangs? Also, you have a question?
Yeah, I was just going to ask about the ketones and the carboxylic acids, because the way I learned them was that ketones were 1750 and carboxylic acids were 1725.
Yeah.
So is the range kind of like in between there?
So yeah, so your carboxylic acids should also be, I would say, between like ketones and aldehydes. But typically you're going to be looking and confirming carboxylic acid stretches with that OH stretch in the 3000 range, just because that's a much bigger and like more obvious and like stretch. But good question. But yeah, the big difference being those aldehyde fangs. Has everyone seen those fangs or heard about them? Looks good. But just to draw it out, so you're going to see like some peak at 1700, and then typically right around where you have your SP3 peak at 33,000, you're going to see a small set of fangs right off of that. So they're going to sort of blend in with that 3,000 peak. So do look out for them. But these are your aldehyde fangs. And hopefully this is more centered. So that should indicate specifically that if you see those fangs, that it will be an aldehyde. No other carbonyls fit that description. But yeah, so that is our IR for us. Are there any other questions before we move on? Okay, I'll take that as a no. We can always answer questions later too. But yeah, so big thing, just to review, you're going to be looking for 1600, 1700, 2200, 3000, and 3500. I know it sounds like a lot, but if you chunk them out, it's not a whole lot to memorize. But yeah, let's look at the next set. We're going to be looking at NMR next. So NMR is nuclear magnetic resonance spectroscopy. So what that really means in a nutshell is that we are going to be looking at protons. So when you look at protons under a magnetic field, you're going to see that they actually they will align within that field, but it takes a larger amount of magnetic field to align a magnetic force to align protons that are heavily shielded by electrons versus ones that are more deshielded are easier to flip. So when you're looking at your NMR graph, you can actually think of this as shielding is highest on the right side, where the abundance is lowest, and the abundance meaning the number of protons affected, versus deshielding effect is highest on the left side, which is also considered downfield for us. Right, so typically we do NMR with two different kinds of protons. We look at carbon 13, which is a carbon isotope with an odd number of protons. You can really only do NMR with an odd number of protons. Or we look at hydrogen 1, which is just hydrogen with one proton. Or one, it's something to do with the mass. Sorry, that's wrong. So we have to have an odd mass. Protons are always protons. But yeah, so we're going to be looking at both 1H and 13C NMR. But first, before we do that, let's talk a little bit about shielding. Okay, let's see this. Oh, perfect. So when we talk about shielding, what we're really saying is, are there electrons surrounding my proton? So the number of electrons blocking that magnetic force. So when we talk about deshielding effects, we're actually talking about when, say that there is something withdrawing those electrons away from your protons. So for example, one common example that we use is aldehydes. Aldehydes have a downfield shift of 10. And the reason being, this hydrogen here, the electrons are getting stolen pretty clearly by this carbonyl. So we're seeing that even though they're sharing those electrons to form a bond, the carbonyl is acting as an electron withdrawing group. So the more electron withdrawing groups you have, the more deshielded something is going to be. So more electron withdrawing, more deshielding. Right? Reversibly, you're going to see things like alkanes or that are more simple. There isn't a very big difference in electronegativity, not a very big electron withdrawing influence. Those are going to be more shielded. Another thing to consider is, in addition to electron withdrawing groups, you must consider resonance. So for example, a benzene ring, if we look at just one hydrogen, this hydrogen gets to share 2 sets of electrons to form this bond, right? However, because we see resonance, one of these bonds is actually not just for this hydrogen. It's actually being flipped between other carbons, right? So that means that we're going to see that this hydrogen actually gets less of the electrons. It's less shielded than it would be with a non-resonant form. So therefore, in this case, actually, we're going to see that resonance causes a shielding effect, a de-shielding effect as well, which is interesting because I feel like typically when we teach you all about resonance, that's like the one thing that like it makes things more stable, it does all of these things, but in this case, it acts as a de-shielding influence. Yeah. So those are really the 2 sort of big things that you want to consider. Electron withdrawing groups will pull things downfield, and so will resonance. Which here, let's pull that up. Okay. So again, with spectroscopy, there are specific domains that we can be looking at. So with IR, I gave y'all like 5 different domains. Spectroscopy, or with NMR, it's a little simpler. Let's see. We're going to be looking at really maybe 4 regions, but it's a little more obvious. Now, let's see. I'm going to draw for a second, but I'll be right back with the mic. Okay, so typically on an NMR, you'll see your line being between 1 and 12, right? So at about 1 to 2, you're going to see alkanes. So those are just your basic hydrocarbons. Oh, sorry. Yes. Perfect. Yeah. So from 1 to 2, you're going to expect your just basic hydrocarbons. So we're just going to draw a propane group, right? So 1 to 2, just basic hydrocarbons. And this is an HNMR, by the way. And then from 2 to 5, we have some interesting things happening. 2 to 3, you're going to be expecting alkenes. From 3 to 4, you're going to be expecting some ethers. You're going to be expecting alcohols between 3 to 6. And also use the numbers that your professors have given you. These are rough estimates, but I know that each of y'all's professors might give you more accurate numbers. You're also going to be looking for alkyl halides. And let's see. And esters are about 3 to 6 as well. And you'll see some ketones in that range as well. Let's hold this. Right. And so now it just sounds like, yeah, you've told us like a million things. Why are you doing this to us? But it gets a little more simple. If you just think of this as your 2 to 6 range, any peak between 2 to 6 that has been de-shielded to that amount is suspect, right? Typically, the way that I like to look at it is that anything that is sort of oxygen, you can sort of lump these together in terms of the heteroatoms. So anything with oxygen, like alcohols, ethers, and esters, as well as ketones, are one set of things you can expect. You can eliminate whether they are that or not based on, first of all, your chemical formula, if you're given one, and also based on your degrees of unsaturation. One of the big hacks is if you see an oxygen and you're trying to figure out like, oh, is this a ketone or an alcohol, is look at your peaks. Well, look at your peaks and look at your degrees of unsaturation. So if you see a peak between 2 to 5 and you're like, okay, maybe this is an alcohol peak or an ester peak, what can give it away for you is the fact that you also have a certain number of degrees of unsaturation that allow you to have a double bond. You're also going to be able to use other resources. So if, for example, your alkyl halides, these ones you can typically figure out using mass spec. But those should be your like hotspot ones for between 2 to 6, right? Next up, you have from 7 to 8, expect benzenes. That is the most common region. And then from about 9 to 10, you can expect aldehydes. And carboxylic acids are at the far end, around 12. But so far, the big things are 1 to 2, regular hydrocarbon, 2 to 5. It's something spicy, but it's in that category of esters, ketones, alcohols, amines, and so on, right? So sort of your carbonyls. So typically if you have, say, an IR, you can actually figure out what exactly that is. If you don't, you'll have to do a bit of guess and check. And then 7 to 8, your benzenes, 9 to 10, your aldehydes, and 11 and onwards, or 12 and onwards, your carboxylic acids. So far, so good? Okay. And now I just realized I have been talking a lot about degrees of unsaturation for someone who hasn't explained them. So let's talk about that really quickly. All of y'all should be using degrees of unsaturation while working through your problems in OCHEM. So I'm sure you're familiar with them. But just as a review, degrees of unsaturation are calculated using the formula that is double the number of carbons, so 2C plus 2, plus the number of nitrogens, and minus your halogens, right, over 2. And so that number that you get indicates the number of degrees of unsaturation you have. Those degrees of unsaturation encompass, first of all, ring structures and also bonds. So the number of pi bonds. So a couple key numbers that you'll be looking for, typically if you see 4 degrees, that indicates a benzene. Because you've got your ring structure, that's 1, and then you've got your 3 double bonds, that's 4. And then other degrees of unsaturation you can typically use as well. Yeah?
Is hydrogen not calculated on that?
Oh, sorry. I added everything together and forgot the hydrogens. You have to subtract the hydrogens finally. And I mean, the definition of degrees of unsaturation, in fact, is the number of hydrogens we're missing. Typically, a hydrocarbon is generally saturated with hydrogens. So every time you add a pi bond or add a ring structure, you're losing a hydrogen. So that's why we calculate that way. But using your degrees of unsaturation and also those peaks, you're able to at least start figuring out what kinds of functional groups you're expecting. The second part to this is also splitting. We should consider, and here, let me pull this up, how our neighbor hydrogens are affecting us as well. So NMR is a little unique because not only are you given the number of hydrogens in a peak, or the number of unique hydrogens that are deshielded, but you're also told a little fact about their neighbors. So for example, if a hydrogen, say you're given a peak that is 3 hydrogens, but it's split as a triplet, that can give you a hit, right? So your basic rule for splitting is that you're going to be looking for neighbors in n-1 you're splitting, right? So if something is split as a triplet, you're going to be expecting 2 neighboring hydrogens, right? So 2 neighbors. And in this case, if you saw a peak that was 2 hydrogens and a quartet, that's your match, right? So you can say, oh, I'm going to have something that looks like a CH2, right, with a CH3, right? And then you can keep on going on. So I think using splitting is also really important. You should be looking out for some patterns. Mainly, I think the biggest one is just looking for triplets and triplet and quartet pairs of 3 hydrogens and 2 hydrogens. But you can also use those to also figure out how your overall structure is arranged. We have a question there and here as well, right? So the number of neighbors is equal to n-1 the split. But you could also call that, I think the way that y'all have been taught is neighbors plus 1 is the amount of splitting equals the splitting. So if you have a triplet, subtract 1, that's 2 neighbors. But if you have 2 neighbors, you're expecting add 1, a triplet. But yeah, it goes both ways. And I know you had a question. Okay. Yeah, sorry about not being specific with that one. But yeah, so you're going to be looking for those patterns. But another thing that you can look for is, for example, symmetry. So say you have, I have one common question that I've seen, I think it was on y'all's quiz, was that you can have, say, 6 hydrogens as a peak, and then you have 1 hydrogen, and these are split as a doublet, and then you have 1 hydrogen that's split as a multiplet, implying maybe that you have a lot of neighboring hydrogens that are the same. You can use that trend to also figure out patterns, such as, in this case, you're expecting 2 groups of CH3, right? You could also expect a carbon adjacent to it to have just 1 hydrogen. So that can sort of confirm some of the questions that you have as you go through. So as you are assembling a molecule, even if you don't initially use the splitting, it's important to be making sure that you can figure out, like, you're aligning the number of neighbors each time. Because sometimes you have something that looks like the perfect structure, it has all the functional groups you want, but your neighboring groups are not right. Another thing to consider is sometimes you won't see alcohols be splitting things the same way. So for example, if you see an alcohol peak with an OH, be also aware that sometimes that hydrogen might not experience splitting the same way. I've seen some professors use that as a trick. It's not always true, but just look out for that as well. But yeah, that's NMR for us. We also have some practice problems where we can sort of look a little more in depth for that. But does anyone have any questions about the material? Yeah.
Can you repeat that oxygen point?
The oxygen point. So yeah, so for example, if you had an alcohol, say right here, so generally if you see the alcohol peak, you're going, that's like 1H, say in the 2 to 5 range, right? You're going to be, oh, sorry, 1H and like, okay, I'm gonna fold this the other way now. 1H in the 2 to 5 range, right? So somewhere between 2 and 5. You might anticipate that you're going to have a triplet. That's going to be a triplet because it's got 2 adjacent hydrogens, right? Sometimes you might not see that. So you might be expecting a triplet, but you see a singlet instead. I would say as long as everything else matches your molecule, that's okay. Do try to see if you can actually find that ideal version, but sometimes NMR can not quite be what you're expecting. So keep that in mind. Any other questions? No. Okay. And then our final spectroscopy is mass spectroscopy. So mass spectroscopy is one that is a little more unique from our other spectroscopies. So far, we've just been looking at, finding peaks that indicate functional groups, right? For mass spectroscopy, we're going to be looking at fragmentation patterns. So specifically, we're going to be looking at how these molecules behave and how you can sort of cut them up and create a stable cation. So splitting patterns are really important. So before we discuss fragmentation patterns, let's also take a slight aside for isotopic patterns. This is also one of the only spectroscopies you can use to figure out what heteroatoms you have. So for example, if you're not sure if you have a halogen or if you have a nitrogen, say like you see an amide peak or an amine peak and you're like not sure, like I see some peaks at 3400, but maybe those are just like my head, right? So you can start checking using your mass spectroscopy. There's a couple different patterns that you're going to be looking for. Some of them are isotopic patterns. Basically, for example, bromine tends to have a heavier isotope in the M+2 category that is about equivalently present. So you're going to see for bromine peaks at the rightmost point, you're going to see an M over Z total peak and an M+2 peak, or an M peak and an M+2 peak that are about identical for bromine. For sulfur, let's keep on the halogen. So for chlorine, we're going to see something where we have about 1/3 for your M+2 peak. It's going to be about 1/3 the height of your M peak, right? For sulfur, you're going to see not quite as tall as chlorine, but not quite too short. You're going to see like a tiny little peak in the M+2 range. There's this tiny amount of that isotope, but not a whole lot, just any M+2 peak that's a little bigger than you're expecting. The other patterns that you can also look for are specifically to do with the mass values. You can look for nitrogen, and I think students always look at me confused for this one. If you have an odd M value, that indicates nitrogen. And by what I mean by odd, I mean odd and even. So for example, if your rightmost M value, right, that's 121, that's odd, right? So that indicates the nitrogen. You're only going to see odd values for the M peak if you have a nitrogen in your molecule. You won't see it for any other element. And this is specifically just because of how nitrogen adds on peaks, like onto carbon chains. The other one that you're going to see that's a bit odd is, and in this case not odd in the same sense, is iodine. You're going to see at one point you're going to see 127 difference between one of your M peaks and one of your fragments. That just indicates that your iodine has left by itself. So, and because it's such a large difference, that will be a little more clear as well. So just be looking out for those. Sometimes your professors might be trying to catch you by trying to find some of those, like if you can figure out those heteroatoms. So be on the lookout for those patterns. But moving on, we also have some fragmentation patterns. Does anyone have any questions before we move on? No? Okay, let's pull this up. So we're going to be looking at a couple different things. First, if you just have a hydrocarbon, right, so we got some fragmentation patterns. Oh, right there. Okay, so we're going to be looking first at hydrocarbons. You can just expect to cut anywhere on that hydrocarbon. The big thing being that you're going to be trying to find stable points that you could put positive charge on, right? Because whenever you cut on a mass spec, you're going to be looking at the protons that form. The more abundant your peak, the more stable your proton is. At that point, the more stable that cation is, right? So, for example, you could have a cut like this, where you've got a secondary cation. You could have a cut on the other side, forming also a secondary cation. So the big things to just sort of look out for when you're looking at hydrocarbons is that you've got some magic numbers. So whenever your professors ask you for fragmentation patterns, or for like, hey, calculate this fragment for me, you're going to be looking for the numbers n-15, n-29, and so on. Basically, your terminal carbon peak is always going to be 12 plus 3, right? So that's your carbon plus 3 hydrogens. And then every adjacent carbon is going to be just 2 hydrogens, so 14, right? So hydrocarbon peaks, I know, are typically the ones that students like the most. They're the most fun to sort of catch and be like, haha, I figured it out, right? But there are some other fragmentation patterns that are pretty meaningful to us. We're going to also look at alcohols and carbonyls. I know that some of y'all might not have learned all of the fragmentation patterns. That's okay if something doesn't look familiar, but it's just good to know. Say you work on spectroscopy later in life, you'll see it then. But yeah, so if you're looking at, say, an alcohol, you're going to be also, there's a couple different patterns. First, one thing that we sort of know about alcohol is that OHs don't like to leave by themselves, but we can make it leave if we form water. So one kind of fragmentation pattern you're going to see is called dehydration, which is exactly what the name states. We're going to see water leave, right? So to see water leave, what we're going to have to do is first form water. So the oxygen on your alcohol is going to go and to tell hydrogen, hey, I can offer you some electrons. Let's form a bond. We'll make water and go away, right? So hydrogen decides like, okay, we can do that. It gives its electrons from its bond to form a double bond adjacent to that carbon, right? Which causes us to find some structure that looks like this, right? And really what this is if y'all remember your E1 reactions from OChem 1, for example, your reaction with alcohols and H2SO4, it's the exact same idea. You're having water leave slightly differently, and you're creating this new cation, right? And something unique about your dehydration reactions is you can also fragment further to cut off a methyl to see if you can form a allylic cation. So you could also further fragment and form a positive charge adjacent to that double bond, which has a lot of resonance. It's going to be a very abundant fragment. So that's your dehydration fragmentation. You're also going to see something called alpha cleavage. So we're not going to go over quite the mechanism for that, but we can just talk about how to identify it. So this carbon over here, this is your alcohol carbon, but adjacent to that is your alpha carbon, your beta carbon, and your gamma carbon. And that's just to name them. For example, you have your neighbors, and then you have your neighbors' neighbors, and your neighbors' neighbors' neighbors. That's too much to say, right? So instead, we just say alpha, beta, gamma. And in this case, we do alpha cleavage. So when we say alpha cleavage, it is what the name is. We're going to be cutting off that alpha carbon. So we will see a fragmentation right there where we cut off that alcohol carbon and we're left with just the other side, right? And say this carbon had something else on it, let's say a methyl. We still have that methyl. We can also do alpha cleavage the other way, such that this is cut off. And you've got a positive charge over there, right? So both good ways to do cleavage, and you can also do dehydration. So the two kinds of cleavage that you're expecting with an alcohol is dehydration and alpha cleavage, right? So it's a little more complicated than hydrocarbons, but not terribly. I know that dehydrations tend to trip people up, but I would just say like try to study that mechanism, recognize how it happens, and that will be really helpful. And also, remembering that fragmentation pattern. Next, we also have carbonyls. Let's see if I can flip this over. So for carbonyls, we have a couple similar fragmentations and a couple different ones. So first, we have alpha cleavage, which is familiar, right? So say I have a carbonyl that looks like this, and we have something like this, right? So alpha cleavage, we've already talked about. This is our carbonyl carbon, right? But its neighbor, we're going to call that alpha, right? So we've got two alpha carbons, we've got some beta carbons, and one gamma carbon, right? So for the first one, we just need to cut off one of those alpha carbons. So we can do two kinds of fragmentation patterns. In one case, we cut off alpha here, right, leaving us with something that looks like this. And in the other case, we cut off the other alpha carbon. And hopefully this is visible, and I'm not just pushing this random But yeah, so we cut off our alpha here. So those are both fragmentation patterns. And now here's the scary one. I know a lot of y'all might have seen the McLafferty rearrangement. I know a lot of people don't like it as much, but it's not bad. So what the McLafferty rearrangement is we have one other one where actually the reason why I've been writing out alpha, beta, gamma finally makes sense. And we're going to rearrange this a little for me before we do the rearrangement because it makes it a little more convenient. So we're going to put our alpha carbon out here, beta out here, and our gamma right there. So alpha, beta, gamma. This gamma carbon has a hydrogen attached to it. So what we're going to see happen is a bit of a rearrangement. We're going to see our oxygen take the hydrogen, similar to what we saw with the dehydration reaction, causing our hydrogen, once again, to give back its electrons, right? Which then we see are actually placed between this alpha and beta. Or actually, sorry, those are just placed there. This oxygen also places it takes its double bond and gives it back as well, just to form that bond. And what you're going to see here actually is a cleavage reaction again. So you're going to see this bond between alpha and beta split. Each takes one electron to form two double bonds. So what your end goal is to form an enol with a double bond between your carbonyl carbon and your alpha carbon, right? And what has left is your beta and gamma carbon. Those form a double bond between them, right? So that's your beta and gamma. Yes.
So who switches where? I'm sorry.
So who switches where? Oh yeah. So let's redraw that. Let's do a different color. You've got your alpha, beta, and gamma, right? And there's a hydrogen over here. So beta, and this is our only gamma carbon, so that's the carbon that we're going to be using. This oxygen so this oxygen will be forming a bond with this hydrogen, right? Hydrogen gives back its electrons, which it has one to give. So it gives back one electron here. And this alpha beta bond also breaks, giving back one of the electrons to beta and one of the electrons to this bond here, right? So basically, actually what we did is we didn't give two electrons, we gave one electron to hydrogen, right? Hydrogen took one to form a bond, gave back one, right? And what this does is over here, we see two electrons here and two electrons here forming a bond, right? However, to form this bond, we had to break the alpha and beta. So to form these double bonds, we have to break the alpha and beta carbon bond. Is that a little more clear? Yeah. Worst comes to worst, if you just want to memorize it, just remember it as we form an enol. An enol is literally a double bond next to your carbonyl. So you're going to be forming a double bond between your alpha carbon and your carbonyl. And you will be converting that oxygen to an alcohol, right? So you've got your alcohol point and a double bond between your carbonyl carbon and your alpha carbon, right? And you've cut off your beta. So sort of like how you had alpha cleavage, now we're cutting off my beta. But we're doing it a little differently. We're reforming a double bond a little differently. So far, so good for everyone? Okay, we're gonna take a slight break. That is all of our spectroscopy. We'll be going on to alcohol reactions, but I just want to give y'all a second to breathe. If you have questions, feel free to ask those now. You can also come up here. either works. But here, it is currently 3:51. Let's take, Frank, what do you think, 10 minutes? Yeah, so let's take 10 minutes and we'll restart at 4. Sorry to everyone online and in person. We were having some technical difficulties, but we are back on board. Okay, so same drill as before. We're just going to be doing, we'll be going through some slides for the alcohol reactions. I'm sure y'all love my pretty handwriting, but this will be hopefully a little easier for y'all to also look through. Okay, and just make sure that your computer is muted if you're also looking at this online. But yeah, so we're going to be looking at some alcohol reactions, some of the other reactions you will also be seeing on this exam. Again, shout out any questions you have. So before we get started with, the reactions that y'all have learned, we also just wanted to go over some of the reactions that you might remember from OCHEM 1. I know OCHEM 1 was a long time ago. Y'all had a snow week and winter break. So just to discuss some of those, first of all, there are a couple different ways you can deprotonate alcohols. You can use alkali metals. You can use NaH, which is a metal hydride. What that creates is an H-, which can deprotonate your alcohol. It's a very strong base. And then other strong bases, right? You can also form alcohols in a couple different ways. First, if y'all remember those alkene reactions from last semester, you can use those to break your double bonds and form an alcohol. You can also use an SN2 reaction to form an alcohol. So when you're looking at synthesis questions and you're trying to get into these reactions, just remember you can use SN2 reactions. You can use those hydrolysis reactions if you have a double bond formed already. Just keep those in mind. Not going to spend a lot of time in depth on these, but if anyone wants to look at something, we can always go back. Also, you can form alcohols by reducing carbonyls. So remember NaBH4 and LAH4. Those are LAH from before. Basically, y'all have learned about oxidizing reagents, but remember you also have some reducing reagents. And specifically know that NaBH is really good at being very selective for only your carbonyls, versus LAH is really great for reducing even your carboxylic acids, your esters, and your acid chlorides as well. And you can also use nucleophilic attack. So basically, if you use a Grignard's reagent on carbonyl, you can also create an alcohol as shown. And remember that typically Grignard's reagents, if they're added in excess, if they're attacking either a carboxylic acid or an ester, or not carboxylic acid, an ester or an acid chloride, you can form multiple of those extra substitutions. You can do multiple attacks. But now let's get into what y'all have been learning. So you've been learning about oxidation, right? And the big thing to remember is that there really are two kinds of alcohols that we're going to be oxidizing. And then also we're going to be looking at aldehydes. But basically the goal of oxidation is to go from a lower form of oxidation, such as being an alcohol or an aldehyde, to a higher form of oxidation. So with secondary alcohols, you're going to notice that regardless of whether they're strongly or weakly oxidized, they're going to be oxidized to ketones, versus for primary alcohols, they can be weakly oxidized to aldehydes, which are a slightly higher oxidized form, or if they can be strongly oxidized to carboxylic acids. And you'll also note that similarly, strong oxidizing agents can also be used to convert from aldehydes to carboxylic acids. So just an overview of some of those oxidizing agents that you'll be familiar with. You're going to be looking at SWERN, which is also called DMSO, DMP, and PCC. So those are just some fun ones to remember. But the way I like to tell students is really you're just looking for your strong oxidizing agents, and the ones that are not strong are your weak ones. So your strong oxidizing agents are first bleach. This is a popular one. It doesn't have heavy metals in it, so it's a fun one to use. And the formula for that is NaOCl. You've got KMNO4, which you might remember from last semester. That was a really good oxidizing agent even before you knew it. if you remember your ozonolysis reactions and your more strongly oxidizing reactions. There's also HNO3 chromate with hydrosulfuric acid and K2CRP07. I don't remember what that formula is called again, but I think it's dichromate. But generally, know your strong oxidizing agents. If it looks like it's an oxidizing agent, but it's not one of them, it's weak. Yeah. And one note to make is that tertiary alcohols are never oxidized. You're never going to see them oxidized simply because to do so, you would have to kick off one of the substituents. And for example, here, none of these are good leaving groups. They're not going to leave with ease. That would not be an oxidation reaction. That would be a substitution or some other. Next up, y'all can also form alkyl halides from alcohols. So these are some sort of hacks. Y'all are used to maybe forming alcohols or adding on oxygens onto alkyl halides, but not really maybe fond of doing the same in the opposite direction. So to do so, you have some magical sort of reagents you've got. And these are phosphorohalides. They perform SN2 reactions, but they're good for specifically converting alcohols. So you'll notice you've got PBr3, PCl3, and PI3, pretty obvious ones. You also have thionyl chloride, which is SOCl2, and that will also perform the same reaction. The difference being that your phosphorus halides will perform an SN2, which causes an inversion of stereochemistry, right? So you're going to go from a wedge to a dash and vice versa. But with SOCl2, you will see no inversion of stereochemistry. So they'll remain, if it's on a wedge, it will be on a wedge, and so on. Next, we also have our Lucas test, which is just what the reason we call it a test is we use zinc chloride with HCl, and we're going to be removing an alcohol, right? So this is basically one way that you can sort of try to reduce your alcohol. However, something that you're going to notice is that I believe tertiary alcohols are most likely to react with this reagent. Then secondary is a little slower. And if you put zinc chloride in a primary alcohol solution, it's going to have little to no reaction. So it's going to not really be showing that same sort of deprotonation. It'll be showing a different reaction, which is your SN2, where you add chlorine earlier. Yeah. So the basic step being that you're going to be seeing, your chlorine added onto your secondary position or your tertiary position. And just notice that the reason why this works a lot better on secondary and tertiary alcohols is because zinc chloride requires causes a carbocation to be formed, and a carbocation is most stable on that secondary or tertiary position. Right. So next, we also have a couple of different ways that we can work with alcohols. Specifically, alcohol, as we talked about earlier, is not a good leaving group. So you can use tosylation to make alcohol into a good leaving group. Just like we used adding a proton to your alcohol is a very forceful way to force your alcohol to leave. But using tosylation means that you can also take off those tosyl groups later if you would like to. So if you ever see that figure, I know it's a little ugly, but the sulfur with the 2 double bonds to oxygen and an OH, that is your tosyl group. And use that to form SN2 reactions using alcohols by converting them to good leaving groups. You can also use protecting groups similarly to prevent them from reacting. So this is a bit different. I know they have similar letters. Tosyls have, you'll typically just see it just called tosylation. TMS and TIPS protect alcohols. So they're not going to be making it into a good leaving group, but they're going to be making it basically unable to do any kind of reaction. So this is really great when, say, you want to, let's say that you want to oxidize your aldehyde, but you want to keep your alcohol the same. You can use TMS for that. And you can also use multiple equivalents. So, and to take that off, you'll just be using, you can just use water. So if you're ever using a reaction and you said like, oh, I'm gonna put TMS on this, and then you're like, oops, how do I get it off? It's just water. Next, sort of in the same vein, are some carbonyl reactions that y'all might have learned. Have y'all learned about hydrates in your class? Or carbonyl reactions? Not sure? Okay, because I might have added a couple more. Does this look familiar? No, okay. In that case, maybe I've skipped ahead. Let's see. But we have talked about esterification in class, right? Okay, let's do that. I know this we've changed some things, so wanted to adapt to that. But y'all have learned about Fischer esterification. So esterification is fun because basically we're able to sort of interconvert using some of the tools that we've gotten from these previous slides. Now we can create carboxylic acids using a strong oxidizing reagent, right? So now with our carboxylic acid, very pretty, you can add an alcohol to basically do a nucleophilic attack on that carboxylic acid and force the OH that was previously there to leave, reforming that double bond, forms an ester. I would recommend understanding the nucleophilic attack mechanism for this Fischer esterification, but it's also like the biggest thing to know is just that you're going to be replacing that OH with the with that alcohol that you now have in its place. So that O and then whatever comes after it. So I think it's a really fun one. Another version you can see is transesterification. It has the exact same mechanism, nucleophilic attack, but instead you're going to be replacing whatever was previously on that ester in that O-R group position with the new O and R group. So the big thing just being that you're changing the R group. It's a really fun one because you just can swap. You just need to draw on what is being reacted. And then one thing to note, I'm not sure if y'all have seen this, but I think it's cool and something that will become relevant to y'all. You can also interconvert from esters to carboxylic acids. So you can use either a strong base with water, or you can use an acid with water to convert an ester to carboxylic acid. So something to note, and that will come in useful in the future. I'm sorry, this is the end of our slides. Are there any other reactions that we didn't cover or that y'all wanted to discuss? Now's a good time to ask. Yeah.
For so for BR, whenever it attaches on secondary carbons, I think it changes stereochem, right?
Sorry. Is that from the PBR3?
I think so.
Okay.
On primary alcohols, I saw that the stereochem doesn't change, but on secondary alcohols.
Are you talking about the Lucas reagent?
I think so.
Okay, let's look at that. So yeah, on the Lucas test, you're going to see that the stereochemistry you'll expect it to change for the primary alcohol, but not for the secondary and tertiary, simply because the secondary and tertiary alcohols are undergoing an SN1 reaction. So
the next slide. Wait, no.
Oh, or if you're talking about, sorry, was it this one?
Yeah.
Yeah. So yeah, we just have that there will be no reaction for a tertiary alcohol, but for a primary and secondary alcohol, you will be expecting when you're using a phosphorus halide, so either phosphor bromide or chloride or iodide, you're going to be expecting the stereochemistry to flip. However, yeah,
Because you see how on the secondary carbon that the BR stereochem changes.
yeah.
But on this side, on the primary side,
it also changes. It's just that we didn't use dashes; we just used empty lines.
Okay. So that's just for bromine.
Yeah. Well, for bromine, chlorine, and iodine, consider those empty wedges to be dashes, basically. The whole point being that if you use a phosphor halide, you will see an inversion. If you use a thionyl chloride, you will not see that same inversion. Any other questions? Yeah? Yeah, we can also send out the slides when we'll be posting this on YouTube, so you'll be able to find it there, and we can also get it sent out. Yeah. Any other questions? Yeah.
Really quickly, I forgot which slide it was, but one of them did react with tertiary alcohols.
That might have been the Lucas test.
Yes, it was.
Yes. So on the Lucas test, you're going to see that zinc chloride reacts best with secondary and tertiary alcohols.
Because of the carbocation stability?
Yes, with the carbocation stability. Mainly because zinc chloride is not going to easily replace alcohol in an SN2 reaction because your alcohol is a pretty bad leaving group. So it's going to be a lot slower, even though y'all have learned SN2 is a fast reaction. It is not quite as fast as using zinc chloride to do that same reaction. Any other questions? If not, we will be going on to the next section. We will be looking at the problem set that y'all received. Okay, sounds good. Let's shift gears and see if I can pull this up. And also, everyone online, you are able to switch between the the papers, but please do not press the arrows because it changes it for everyone, including the people in the room with us. So you should also have a copy of the PDFs. They should have been emailed to you, so you can also find these problem set questions there. Let me see if I can make this bigger for everyone who's in here. Let's fix this out. Perfect. Frank, were you thinking of doing the practice problems, or what are your thoughts? Otherwise I can run through some of them. Yeah, okay. So we're gonna go through some of these, and I'm gonna actually be doing some more innovation with our technology, even though maybe we should not. Let's see if we can. I'll go through the first couple pages, and then we'll have Frank, our lovely tutor, also come in and follow. So you get to hear someone else's voice. Oh my God. This is gonna work out, I promise. We're gonna make it work. Okay. So, I'm not sure if y'all had a chance to look at the problem set, but we'll do up the first page together. And the way we're gonna do this is I'm gonna ask y'all questions and you're gonna answer them. And if you don't, I will be picking on people. It's gonna be a lot of fun for everyone. But let's see. And also, fun fact, I don't know how to use the eraser on this, so we're gonna try to be as careful as possible with that. But looking at this first problem, we're gonna be ranking the indicated bonds. So those are those little highlighted bonds by the frequency on an infrared spectroscopy graph. So specifically, you're gonna be looking at that carbonyl on the first one, the carbon-carbon double bond, the carbon-carbon single bond, carbonyl bond on the fourth, carbonyl on the last one. So whatever's highlighted. I'll give everyone a minute or two to solve it, and then we'll start calling on people. Huh? Yeah, so you can work together. So if you want to talk to each other, this is not an exam. You're studying for that one. So feel free to discuss. And if you have questions, ask each other, ask us. We'll be trying to answer those as well. Okay, and I'm going to give us until like 4:27 and some change. It'll be good.
You have to click on the pen.
Uh-huh.
You can change it to erase
I
it.
can change it. Okay, and for the sake of time, I'm gonna cut y'all off, but hopefully you have some ideas, at least maybe 1 in 5. And actually, that's my question to y'all. Does anyone know, so we're ranking based on IR. Does anyone want to present, let's say, number 1 to us? Yeah.
So I'm not exactly sure what's the specific frequency, but I know that initially we're thinking that the oxygen carbon bond is going to be around 1700, but since resonance is possible, we're going to be lower than 1700.
Right. So we said that because of resonance on our ketone, we're expecting that to be a little lower than 1700. Perfect. We're expecting this first molecule to have an IR peak of less than 1700. If I can make that closer. But yeah. So we're expecting that one at less than 1700. What about the second molecule? Anyone know where we're expecting that carbon-carbon double bond to be around? I didn't quite mention where it would be actually, this peak. Yeah.
You want
Go ahead.
Okay. Wouldn't it technically be in the fingerprint region though?
Yeah, so your carbon-carbon double bond is around this fingerprint region, but that also tells you something. That tells you that it is going to be pretty far right? So as we said before, our double bonds, our bond order matters, right? So our double bonds tend to be around the 1700 region. So C double bond O, for example, and then your carbon-carbon double bonds tend to be around 1600. Those are pretty low. So we're going to just say low, right? Same thing for our single bond as well. Now let's talk about this fourth one. Where would that be? Anyone have any theories? I'm gonna call on you with the high.
Oh man, don't do that.
You gotta try.
So this one always freaks me out because like I feel like it can resonate
Uh-huh.
with the oxygen, but like I always get this one specifically wrong. So
Yeah.
I'm nervous on the fact that you called me.
Well, it's an ester, right? So what did we say about the energy levels of carbonyl groups?
I wasn't here for that.
Oh, that's okay. Okay, well, we have like all of those notes out as well, if you want to take a look at them later. But we said that actually esters have the highest energy of the carbonyl groups. So we're going to be looking at, when we look at carbonyls, we're going to be looking at esters, then aldehydes, and then ketones. Oh, and this is going to come out perfectly because I'm really hoping it does. But so you're going to be expecting carboxylic acids also to be around like between those ketone and aldehydes. But yeah, so esters are a little different. I know that it's a good point that they can resonate. I did say earlier that resonance shifts things right. However, it's not the same case for esters. The reason being, amides you see do get shifted right. The reason is that nitrogen is a lot less electronegative. So actually it doesn't have, it has more of a resonance effect versus this oxygen that is adjacent to that carbonyl on the ester actually has a bit of an electron withdrawing effect. So it's actually causing a higher bond energy. So great question. Esters should be higher energy though. So you'll be expecting that around the 1735 range. What about this last one? I saw a hand up earlier. If you want, or if that was a question, you can ask a question.
1720.
1720? Perfect. So that would be around the 1720 range. So we're saying that we know that these carbon-carbon bonds tend to have a lower bond energy than carbonyls, right? And then we said, I believe that our esters tend to be pretty high. Our ketone will be shifted to the right for our resonance structure right here. So anyone want to give me a guess for the order of everything? Yeah? You, but we'll ask you the next question next.
I put 3, 2, 1, 5, 4.
Okay, perfect. So 3, 2, 1, 5, and 4 is correct. So your carbon-carbon bonds are going to be a lot lower, given that they're not even with carbon and oxygen. A bond between carbon and oxygen has a higher energy than carbon and carbon. So that puts them far below, and that double bonds have more energy than single bonds. We talked about the reasoning with the resonance for the ketone, but everyone feel solid on that answer? Perfect. So we're gonna scroll down, and it's not gonna be as awful as when I was using the document camera. Okay, so let's see. We've got a couple questions. This one, and also I just saw a question that, do we care about the carbon-hydrogen bonds? In this case, I indicated the carbon-carbon bonds specifically, so that's why we're addressing those and not the hydrogens. For B, it has a similar idea, so we'll do B. We might skip C, but if anyone has questions, we can also talk about those later. So B, we're looking at ranking the following structures based on how downfield shift would occur. So this one is a bit similar. We've already gotten into the vibe answering questions. So I'm gonna give y'all a minute. We're gonna come back to y'all at 4:36. Take a second to take a stab at that. It's pretty similar to how we did the last question, except resonance is now shifting things downfield, right? So keep that in mind. If you want to do this. Also, bonus points to anyone who can identify the third molecule. We'll talk about it.
So TMS, right? Tetramethyl.
Yeah. So we'll talk about that. Yeah, so yeah, I think it's also been shown up there. It's off my mic on. Yeah. So we've got some guesses. It is TMS. We talked about it with the alcohol reactions, but you might know why we use TMS in H&MR, so consider that.
Isn't TMS only, I forgot the term of it, but it's like the baseline?
Mm-hmm.
It like zeroes out versus.
Yeah, so we're answering my questions really quickly now. So TMS is the 0 for H&MR. So that should tell you how we should be considering that. So if TMS sets your 0, it's going to be probably less downfield, right? Okay. Anyways, it is 4:36. We're going to do a bit of a speedier round with this. Does anyone have my set of 5 answers? And we can go over why. If not, you can give me 1 or 5. Give me one of the extremes. So we have that 5 is the aldehyde. Great one. 5 is indeed the aldehyde. You'll notice I am really good at writing. Okay, perfect. That's 5 twice. But just like we said, aldehyde is going to be around that 10 region. That hydrogen next to the carbonyl is going to be super deshielded because of the carbonyl adjacent to it, right? Anyone have 1 for me? Oh yeah, we have TMS. We just talked about that. Sorry. But yeah, so now we're left with 2, 3, and 4. Anyone want to give me a guess of how those are arranged? Yeah.
Benzene ring 4.
So benzene ring is 4. Who has 2 and 3?
Would the last T be 2 and 3 by order?
I'm not sure if everyone heard it, so I'm going to ask if anyone else has the answer. For 2 and 3? I know we appreciate the answers. Okay, we have 1 up here. So 5, 4, 3, 2. So actually, in this case, I believe that might be it. So actually, it's not 2 and 3 directly. It's 3 and 2. The reason being, this is a double bond. Specifically, this is a carbon-carbon double bond. You'll see that alkenes tend to be located between 4 and 6. Ketones tend to be located around between like 2 and 4. So it's a small difference. I didn't do much better by adding resonance to the structure and bromine there to make it more complicated, but we will be ranking that as 5, 4, 1, and 3. Yes?
I have a question. So, I actually got the other way around because you can resonate the double bonds on the alkene, so you guys have a positive charge, so it's more deshielded, so it's more downward. If that makes any sense.
So that is true. So you are going to see that peak shifted further left. But what I generally keep as a rule of thumb is that you're going to be looking for where that peak would be initially and then shifting it from there. Both of these have deshielding effects. The alkene has a bromine on it, and that second one does have resonance, but because a ketone peak would be lower than an alkene peak, we keep that order. Yes?
That would also have an alkene.
Huh?
That would also have an alkene.
That is true. Ooh. That's a bad question then. That's on me. I would say in that case, do not use those 2 answers, but do use the conversation to supplement your learning. That's my mistake. We'll update that when we also send out the problem set with the key. Yeah, we do have an alkene. So in this case, what I would do if I were to rewrite this question and be a better problem set writer is I would take out that resonance structure. So for future notice, if you ever write an OChem exam review, do not do that. But yeah. And also the comment that was made, if someone didn't hear it, was that the ketone also has, no, not the ketone, the ketone also has an alkene on it, so technically you would see an alkene peak there. So, my mistake. But your 5, 4, and 1 should be accurate. Okay, so what we're going to do is we're going to switch gears a little and do some spectroscopy. Frank is going to be coming up now, so you'll have, you'll be able to help out. Okay. Well, and we're going to see if we can share our files. Perfect. Oh, for C, So we did not go over C. We will be sending out the problem set for that question, but if y'all have questions, oh, one note, actually the second and third molecule have maybe the same number of signals, so that's a mistake on my part as well. Add a methyl to the third molecule. And we'll fix that later. Okay, Frank.
Alright, let's start with number 4.
And I can do that.
Okay. Alright, what's the first thing we should do? We're given the formula and it's a spectroscopy question. Yes, degrees of saturation. So,
Oh, I can do that. And I can put you in pen mode.
very cool. Okay. So yeah, 2 is 9 is 2. So we got 18 plus 2, 20 minus 10 is 5, is 10 divided by 2 is 5. Right? So we have 5, right? Okay. Well, we have 5 degrees of saturation. So whenever we have anything more than 4, we could, it's safe to assume that we would have a benzene ring.
I can figure it out. Okay.
Okay. All right.
Yeah, you might also just be closer to here, if that's possible.
Yeah. Good. All right. So looking at the degrees of saturation, we have 5, right? So we already have 4 with the benzene ring, and so we also have 2 oxygens here. So if we do have oxygens and if we have more than 4, it's safe to assume that the last degrees of saturation would be a carbonyl. So let me draw that right there. Okay, got a carbonyl. Looking at the actual NMR, we have 3 at 4, 3 hydrogens at 4, 3 hydrogens at around between 2 and 3. Okay, so whenever we have a peak at 4, usually with 4, that is going to be your ester hydrogens. So let me draw a ester. Okay. When I say ester hydrogens, it's going to be the one adjacent to the oxygen with the lone pairs. So right over here. These are your hydrogens. Okay. And we have 3, so that finishes that one side, and so we still don't know what's in here, right? However, if we look at what we already know, we do have a benzene ring. We can't have the last 3 on this location,
because otherwise we complete the molecule when we haven't put in the benzene ring yet. And so we can actually put the benzene ring at that position. So like right over here. So that takes care of this 3 hydrogen peak. Now we need to figure out where this 3 hydrogen singlet peak is. Now, how many carbons do we have currently? We have 1, 2, 3, 4, 5, 6, 7, 8, and we have 9 right in the formula. So we're missing 1 more. We're also missing 3 more hydrogens, and so that we can say that that's a methyl group. Now we have to arrange it in a way that we would have 2 hydrogens be symmetrical. Okay, so we could have the 2 hydrogens over here be 1. These other 2 hydrogens can also be symmetrical. And the last place we could put this methyl group would be at the tail, or the opposite end of the benzene ring. And so your final molecule would, where's this? Would be this. Any other questions? Okay. I'm going to. Let's go to number 6. How many carbon signals? Oh. With carbon signals, we would see NMR. We would look for unique carbons, or is it hydrogens or carbons? With carbons, you have to do like unique carbons. So if we look at the line of symmetry that we currently have, it's like right around like over here. So counting the carbons, we have 1, 2, 3, 4, 5, 6, and 7. The other 2 over here these 2 are the exact same carbon as the one above it because of the symmetry. Did I answer your question? Okay. Okay, moving on to question 6.
Huh?
Okay. Okay, go to number 6. We do have we have IR and we have CNMR. Alright, so I'll go over this real quick, but if we do our degrees of unsaturation, right, we would do 7 times 2, which is 14, plus 2, that's 16. 16 minus 8 is 8. Divide that by 2, we should get 4. So for degrees of unsaturation, you could say that that is a benzene ring. We would have a benzene ring. Okay. Now another thing you can see here is we have a huge peak right here, right? And this will be your alcohol, right? Okay, so if I just stick my alcohol in this molecule here, we can see that we still don't have 7 hydrogens. We currently have 6. So we need to figure out where that 7th carbon is. So that's where this CNMR comes into play. With CNMR, we do have 3 signals right here. Okay. I guess another way to think about it is, let me erase this. This can be one of your pieces. Your other piece is an alcohol. And so we could just say that the last piece is in the middle. Like that. And that would be a molecule. So we don't actually have to look at the CNMR for this. Any questions? Yeah.
If you were to go by the route like the quartet triplet thing, how would you do this question?
So this is CNMR. With CNMR,
You can divide
divide by 20.
for the numbers, ppm, to convert to HMR.
Oh, okay, yeah, divided by 20.
So those are between 6 and 7.
Okay, yeah.
Got a lineup.
Yeah, so this is 6 and 7. And yeah, so this is 22. What did you say was this one is?
That would be around 3.
Okay. With CNMR, we do, I think this is is this a triplet?
CNMR, I think, actually those are 4 peaks. There's 1, 2, 3, 4.
Well, I would say usually you wouldn't actually look at the CNMR to look at splitting. It's mainly just used to look at the different kinds of carbons, I would say. That's how I usually look at those, that CNMR. But here we do have 3 different peaks. Is this CNMR, right?
That's a CNMR.
Yeah, so.
And also, please don't change the slides.
Whoever's online, please don't change the slides. Okay, thank you. Okay, so we do have 1 carbon here, 2 carbon. The second carbon would be here, and then because these 3 are essentially they're essentially counted as the same because they are far apart from the alcohol, that they kind of share the same similar properties, so that's why we do show up as 3. That's why these carbons right here are really close together because they share the same properties. Let's do number 7. This is tricky in that they don't give you a formula. Now, how would I approach this? Well, let's look at the mass spec, right? If we look really closely, we see a peak. The highest peak right now is 86. That would be your parent peak, or your M plus peak. Okay, and then we can figure out all these different peaks. So this would be 43, This is 58, 71, and then I think that's good enough for now. Okay. Now let's look at our IR as well. We can see at IR we do have a peak right here. It's at 1700. So we know one of our pieces is a carbonyl. So we don't know what's in the left or right side of this carbonyl. However, now let's go back to this MS. Now if I do some math and do 86 minus 71, that should give me 15. Yeah, 15. So 15 just means that we do have a methyl was cut off. So you could say this is one of our pieces, a methyl. Now going to 58, if you do 86 minus 58, that should be, let me make sure.
I think it's about 28.
Is it 28?
Yes.
Okay, yeah. So 28 would be from 58 to 70, 86. Now, if you go to 43, you could do 86 minus 43. I think that is, that's just 43, yeah. And so 43, that just means we have a fragment that, we took off a 3 carbon fragment. Okay. So we have 3 carbon fragment. We still need to figure out what this 58 is, right? And so what you can do is, let's look at this molecule. We already know it is a ketone. And so if, by removing this methyl group, we could say that we do have a methyl in one side. And the rest, we can say that we have a this 3 carbon group right here. Now with 58, since we have a carbonyl, we could try to see if McLafferty would, if doing a McLafferty would make this a 58. And so in order for us to have that McLafferty, we need to have enough carbons in this chain to have a gamma. So let's see, alpha, beta, gamma. Okay, and so if we do that McLafferty rearrangement, our piece would look like, we have this, we would form this enol, okay, and then if I calculate the weight of that, is 58. So this would be a 58. So that just means that McLafferty does happen. And so this would be our minimals, at least the structure that we have. Now, because we have this 43 peak, we still need to figure out where this 43 would be. And the only way I could cut 43 and still be stable is right over here. 2, 3, yeah. And so if I cut off this piece right here, that should give us, let me see. That should give us 43. Yeah, so this portion here would be our 43. And this is also 43. So this satisfies our 43 peak. Okay. Do you guys have any questions on how I did that? Okay, cool.
Well, if you're saying that both of those are 43, then why? Are you saying that when we subtract, one of them is when we subtract 43, and then the other one is when we're always left at 43?
Yeah, so when I say 43, that's just the weight, right? That's the weight of the fragment. And because we have a high peak, that is our base peak, right? The highest peak. It just means that we have more weights that are 43. And so we could either fragment on the left side or fragment on the right side. We would still get a 43. You could either get a carbocation on the left side or a carbocation on the right side. And so either way, you'll still get a 43 when you cut it on the right side.
Okay.
So, did I answer your question?
I think so.
Other questions? Yeah.
For McLaughlin rearrangement, where do you cleave?
The fast way to do McLaughlin, which I would say to cleave between the alpha and the beta. And so if this is our molecule, this is the alpha, and this is the beta, right? And you just cut it right here, and then what happens to the pieces is anything, the beta and the gamma would turn into a double bond right here, and on the left side, this carbonyl you'll have the double bond kind of like over here. So this is the alpha. Oops, okay. Yeah. Did I answer your question?
Frank, could you draw the McLaughlin rearrangement really quickly for us?
Yeah. So McLaughlin. So McLaughlin is when you have a carbonyl. A carbonyl that has enough chains for gamma carbon. So right over here, from over here. So what happens is these oxygen will grab the stage, and then we do what happens is like this single electron will merge with this bond right here, and then this bond between alpha and beta will split off into two over here. This is really that. Okay, let me draw the arrows. So the alpha and beta bonding pairs get split apart. So that's why they cleave right here. And then one of the electrons will finish it off, making a double bond on the alpha and the carbonyl. This is your remaining. This is what you get, and then this is will be the alpha, beta, the positive charge will be at the oxygen. Okay. Okay, and then we'll do one more. We'll do number 8. It's kind of tricky, and so let's see if you guys are able to do it. I'll give you guys like, say 5 minutes. Number 8. So, yep.
Yeah, I think so.
And if y'all need like any of the peaks,
Is it 71, 57, 43, 27?
which one?
Okay, great. There's 71, 57, 43.
43 and 27.
So this is just a 57.
Yeah, that should be 57. And your MP should be here around that number. So that should be 114.
let me get started on this. Hopefully the writing will be better. So let me put the numbers for the MS. So we have 114. You have a 99 over here, 71, 57, 48, and I'll just go from there. I'll just use those. Let's look at our, yes, that is 48. And then going to the IR, we do see peaks over here.
Frank, the peak is 43. Yeah.
Oh, my bad. Yeah, that's 43. Okay, thank you. Okay, so we do have a 17, or yeah, 1700, or about like 17, between 17 and 1800, closer to 18. So whenever we see something that's closer to 1800, we can say that that is a carbonyl, but because it's shifted to the left, we can say that we have a ester. An ester, okay. This other peak that we have right over here on the right, right over here. That is about 16, closer to 17, maybe like about 1660-ish. One of the with 1660, that can be either your amide peak or your double bond peak, which is like just like a double bond. With amide, because we don't really have any peaks past like 3000, to signify as if it's a primary, secondary, we can say that it is a double bond peak instead.
What else tells us there's no nitrogen in this?
Okay.
What else tells us that there's not a nitrogen on this molecule?
We also don't have any nitrogens in like 2200. We don't have any peaks of the CN group. So
The mass spec.
and a mass spec too. This is a even number. Okay, so with that, let's look at our HNMR. We have a 3 hydrogen triplet on the very right. So we could say that we have a methyl with 3 hydrogens. Okay, and it's triplet, so it's neighboring with 2 hydrogens. Okay, now we introduced these 2 hydrogens. Now we do see 2 hydrogens. This is a 2 hydrogen multiplet, and then the one on the left is a 2 hydrogen triplet. This has to be at least a quartet because we have 3 hydrogens already, and so we could say that this 2 hydrogens is actually the one over here. And if you look closely, it has 6 peaks right here. So 6 minus 1 is 5, so it's neighboring 5 hydrogens. So the other 2 would be right next to it. Okay. Now we introduce 2 more hydrogens, and this 2 hydrogens is neighboring 2 other hydrogens. And with this other 2 hydrogen peak, it is a triplet, and so this 2 hydrogen satisfies what we have already. So there's no more hydrogens. The next carbon will not have any hydrogens. Okay. Now we do still have the ester here. Now whether or not this piece goes on the left or the right side, we have to look at where is these 2 hydrogen, where are they located? Now with esters, if we have a peak at 4, it talks about it's about hydrogens that are on the ester side, or where the oxygen side. However, the 2H triplet is more on the 2 to 3, and so which is the carbonyl range, and then that just means that this 2H triplet will be on the carbonyl side. So the molecule is actually like this, and we still don't know what's on the right side. So let's keep going. We still have this fragment, or not fragment. We have this piece of alkene, and so we can try to see where the alkene is, and I do see 1 or 3 hydrogens here. 1 hydrogen is a doublet, 1 is a doublet, and 1 is a quartet. Yeah. And so if we put this alkene on our piece so far, it can either be one of the 2 ways. It can either be like this, or like this. Now, if you look at the bottom one, right, it gives us 2 hydrogens over here, right over here, whereas the one on top gives us 3 distinct hydrogens. And so because it gives us 3 distinct hydrogens and not 2 that are the same, we could say that this is the molecule that we have. Okay, anyone have questions? Yeah, so the molecule is like this, an ester with a alkene. And someone asked, why is it a quartet? These 2, the one at 5,4, are doublet. This is the 2 hydrogens that are splitting each other. And then the hydrogen on top, or the lone hydrogen here, it's splitting with these 2 other ones. And yes, 2 other ones, and it has 2. So actually it has to be a triplet, right? Okay, okay. So one hydrogen has the double, the other hydrogen has the doublet, and this other hydrogen, the lone one, it has a quartet because it's next to two hydrogens, and that gives it 4. So 2 times 2 is 4, and that's how you would do how you would split alkenes. Any questions? Yeah.
Are you really using the mass spec in this question?
What is mass spec? Not really, but you could, and you could. It's just more information. So, I mean, if you want to go to get that route, if you do the differences between the peaks, 114 minus 99, that is 15, which is a methyl. And you can find a methyl on the left side. With 71, we have 43, and then 43 is 3 hydrogens, and we have 3 hydrogens here, and we would split it between the carbonyl and the alpha carbon. 57, you just lose 57. That is, since 57 is either a 4 carbon chain, however, we don't really have that here. However, 57 is it's also talking about splitting it from in half like this with so this gives us 71. And then since we already know what this was, and we were really trying to figure out the right side would have a 57 weight. And so you would need to use HNMR to figure out how that double bond is laid out. And then 43, that is 115 minus 43 minus 71. So it's when you lose this 71 over here. Let me calculate this. Okay, yeah, this is actually 43, not 57. So with the 43 and 71, they're kind of linked together. It depends on which one has the carbocation. Now with the 57, that should be I think that's just splitting it on the other alpha, between the other alpha carbon. Yeah. So we have this fragment that's times 3. I'll be honest, the 57 is kind of tricky at how you would split this up, but the rest of these peaks should line up to the molecule. Yeah. Yeah. So
The peak between 8 and 7, that's not a benzene.
8 and 7, no, that's not benzene.
What is it?
That is the hydrogen between the ester oxygen and the alkene.
And just remember that things are also being pulled downfield by the ester itself. And another thing that you can use to eliminate the benzene peak, or that as a benzene, is that you would expect a mass spec of M-77. The mass of benzene is 77. Given that you don't see that, that also eliminates benzene from your sites.
Okay.
In that case,
and let's do number 9. This shouldn't take too long. It's just some reaction equations. We're going to part A. We do have the tosyl chloride, right? That just changes this OH to OTS, and we have NaCN, which with CN being your nucleophile, OTS your leaving group. So this doesn't reaction, a SN2 reaction where you invert the stereochemistry. Second reaction, we do have the Lucas reagent, and with Lucas reagent, we know that it changes OH to chlorine. And we have MnO2. Thing with MnO2, it's kind of tricky in that it oxidizes certain alcohols. It oxidizes
alcohols alulic.
Yeah, alcohols are alulic or benzylic. And so this alcohol will actually turn into a ketone, whereas this alcohol will stay the same because it's not alulic or benzylic. And part D, SOCl2, right? That's also just adding or changing the OH to a chlorine. But the property of SOCl2 is that it does not change the stereochemistry. And the next one, NaH. If you think of NaH, Na is always positive. That leaves H to be negative. So it's kind of, it's actually acting as a nucleophile, where it actually, or more so like it's acting as a base actually, where this H will grab this H, making this alcohol into a nucleophile, or this alcohol into a nucleophile, where this alcohol will do a SN2 attack at this alcohol, this molecule with a bromine, leaving you with this molecule. And then the part F, PCC, that is your weak oxidizer. And so with what we have right here, which is a primary alcohol, with weak oxidizers, it's going to add one bond to oxygen. So instead of here, we currently have one connection to oxygen, we're going to increase it to 2 connections. And for 2 connections will be your aldehyde. Okay. And then your last question is, you have an ester and you have an alcohol, and whenever you mix those two together, you have a carboxylic acid and an alcohol. When you mix those together, these two OHs combine into one single oxygen. And this should be your final product. You zoom out. Does anyone have any questions on any of them? Yeah. Yes, one O and 2 H's will leave to be inform water, and that's how you get the esterification. I think we can have time for like one more. Let's go back to number 8, where it talks about IR. Now here, let's look at the peaks that we can find here. For number 1, if you look really closely, you do see a peak right over here. Right, we have the peak right there, which is around like 1600-ish. However, we are accompanied by these 2 peaks over here, and whenever you see peaks over there, will signify a amide or a amine. Now, because we have 2, that just means that it is a primary amine or primary amide. It wouldn't be an amide actually, because we are missing the 1700 peak-ish. Right. Well, let's look at our options. We know that there is a primary amine. We have 1600 peak right here. The options that we have that contains a primary amine would be option B. Okay, any questions? Okay, moving on to the second one. With the second one, I do see a peak at about 1700-ish, and I do see these things here at about 2700 to 28, and that just means we have aldehyde. So going back up to our options and looking for an aldehyde, we do an aldehyde at A and an aldehyde at G. Now, the only difference here is that we have a benzene ring, and here we do not see a peak at 1600, right? And so this would be G. Okay. The third one, the first thing I see is this huge broad peak here at 3000. Remember, 3000 is carboxylic acid. Right. Carboxylic acid, and this peak here is about 1700. Okay, going back to what our options here, we do have some options. We have a part E, or option E and option H. Again, similar to what we had on the previous graph, we are missing a 1600 peak. This 1700 peak just kind of just confirms that we have a carboxylic acid, because carboxylic acid has a carbonyl, and that leaves us with option E for the third one. All right, the last one, looking at what we have, there is a peak here around 22-ish, 2200-ish. So that could either be two options that we could have. It could either be a CN group, a CN functional group, or a terminal alkyne. Now, let's look at our options first. Okay, so it could either be I or J. It wouldn't be F because IR doesn't detect internal alkynes, just terminal ones. And so, looking at this, in order for us to have I, we would need to have that 1700 peak, or 1600 peak, which we do not. We don't have it over here. So this leaves us with J, where it's just the CN, nothing else. Any other questions? Okay. We will post the key, and that should cover the ones that we aren't able to cover. But if you guys do have other questions, you can just come by afterwards and you can tell us your questions. And if you're online, if you do have questions, just make sure you make it known in the chat. And good luck in your exam.
I also have the papers I used for my notes earlier. If you want a picture of those, you can. Also, won't have my feelings hurt if you don't want them. So I'll put them here.
Can I see the answer for number 8?
Yeah, 8 is this one right here.
Are also going to be shifted further. And then in addition to that, there is also
like this, there's like a quartet with 1.
I would say it's because when you have a double bond, an alkene, each hydrogen on the alkene is a doublet, and so
Oh, okay.
yeah,
Okay.
each I guess yeah. So
That makes sense.
yeah,
Yeah.
these
Okay.
two would have a doublet with this.
But they're not like chemical
Yeah.
equivalents. Okay. Thank you so much. How will I be distributing the notes that we went over today in the presentation?
Are you talking about the PowerPoint slides as well?
Yeah.
It should be posted on or it should be linked in the YouTube page. It should be. Let me double check.
Where's the PowerPoint? I have it here, but we're gonna be putting that on our YouTube page after this. So if you have a specific slide you want to take a look at, please do.
I just didn't know what the YouTube page.
Oh yeah, so we have a YouTube page. It's called Peer Tutoring at UT Dallas. This is going to be posted tomorrow morning probably. But you can also look in the descriptions for the problem set, the key, and the slides.
Okay.
Yeah.
I don't know who you would tell about this, but there was like a cup sitting behind us that was like full of ants. So they're having a little party back there. I don't know if it's not this. This is mine. But yeah, there's like a bunch of them on the floor. I don't know what to do about it. But you know, maybe you guys know someone or
Thanks
something.
for letting us know.
Yeah.
I think we'll try to see if we can tell someone about that. But yeah, thank you. What's up? Yeah. So yeah, you're back here. Sorry. So we have one line of symmetry that way, and that really is our one line. I would say if you're not really big on the lines of symmetry, one thing that I like to do is I also like to mark the different carbons by how they're unique. So like a small thing just being that I have something drawing, something like this, and then one card, right? So what I would do is I would go down to each carbon and I'd ask like, is there a similar carbon? So this carbon or this carbon right here has a similar carbon right here, right? But does it have any other similar carbon? No.
So if you cleave something right here, right, in an alpha cleavage, would this cation go over here, or would this cation become, would it be something like this? Would it just be an OH right here?
This one is far.
No. Well, the thing is with what you have currently, the lone pairs on the oxygen will resonate to turn this positive charge to make it neutral, and then you'll make a triple bond with the oxygen, and where the oxygen will have the positive charge. Yeah, and that's still stable, even though it doesn't look like it is. But with this configuration, all the atoms are octet, and so that's why that's a favorable.
I figured because if you had a cation right here, you know, this would have an octet, so I figured that wouldn't happen. Yeah, thank you very much. I think.
So that's a resonance, another resonance part of the other one, but you can still get credit if you do the other resonance.
And also, like for the most abundant fragments, would McLafferty be one of the most abundant? Like,
Yeah.
Like how? Okay. But this would be more abundant, right? The alpha cleavage or the McLafferty's? I don't know.
Do you want me to pull it for?
I would say the McLafferty is going to be the best one, because with McLafferty you're not it's easier. It's just easier to do. It's easier for McLafferty to happen whenever you have that many chains of carbons on an oxygen.
Yeah.
The others. Would you? Yeah. So, well, here it's not really asking you exactly which one's the top 3. It's just telling you just the number. McClafferty would be a abundant peak, but we wouldn't know compared to the other 2, or the other 2, which one is the more abundant unless we actually see the graph.
Oh, really? Well, B is asking which one is the most abundant out of these 3. So
that's a bad question, but it will be McClafferty.
Oh yeah.
You can I guess assume that it's going to be McClafferty. Conceptually, you don't have to know why. It's just with McClafferty, it's
just more stable.
Yeah, I guess it's more stable. You're not really, your fragment that you're leaving behind is not it's not a radical, right? Because when you do fragments, you get a carbocation and a radical, right? But with McClafferty, you get a carbocation and a neutral piece, right? With a double bond. Yeah.
So you get a cation, but you don't get a radical?
Yeah.
Oh, okay.
So that's.
Oh, is that what like this thing was about? Like they have the plus right here? Well, no, it doesn't make sense.
Yeah.
So you just be left with like a double bond? Is that? Oh, okay.
Atoms are not symmetrically substituted on the double bonded.
Okay. And then like for number 3, like this one,
because I would say like
would it be like just this alpha cleavage? Yeah. Okay.
Yeah, alpha cleavages are really stable for ketones. Yeah. Ketones and aldehydes.
Because
Thank
this
you very much.
has.
Oh, and also,
So you're gonna
do you
expect
have
the
that
trans to be
slide?
different
I want
from what I'm
a
looking
slide that went for the alcohol reactions. I have it. I just wanted to
trans is
look
going
at
to
something.
be a higher frequency. So for the left.
Yeah, which one?
And your cis is going to be a
The
lower frequency.
oxidizing agents. Yeah.
Here.
It seems to make a wave is this peak right here.
So
17.
I don't know who that
Yeah, let's
student
check
is, but
T
the other one that
for
was
that.
helping teach
Should
us.
not-
But she was saying like a good way
I
to
would
go
say
is
it's
like
probably,
just know the strong oxidizing agents
$3,000
and then assume
Right.
everything else
So,
is a weak
if you put
oxidizing
these two
agent.
Yeah.
Yeah. Are these all the strong oxidizing agents that we should know?
To the left.
Or is there like more? Is there less? Like will I be? I'm pretty much asking, will I be good if I just memorize those?
I would say that if you have a lot of oxygens, it's a strong oxidizing agent.
Oh, that makes sense.
With the first one, NaOCH, I think that's you'd have to memorize that because that's just bleach.
Yeah.
That only has one O, but bleach is pretty strong. So you can just with knowing that bleach is a strong strong chemical, you can just say it's a strong oxidizing agent. Yeah, but if you notice all of them, you have oxygens at least 3.
Yeah.
Right. So yeah, like especially dichromate at the bottom. So that's an easy way to remember it. Just if it has a lot of oxygens, it's a strong oxidizer. If it's named by someone or just abbreviations, we.
All right. Thank you very much.
Of course. Thank you, Frank.
Yeah.
That was the time.
My computer's so loud.
Huh?
My computer's. It's just taking off.
Are you guys gonna do this for all the exams?
We will be doing it for the next exam, but not for the final.
Okay.
We also have exam reviews uploaded on YouTube, that same link, through tutoring at UT Dallas. So if you want to look at the previous year's exam reviews, or we have some problem sets that are different. Some of these questions are straight from like older problem sets, but we've given these reviews a couple times, so there are some resources out there.
Because I really like this.
Yeah, I'm glad. But yeah, we'll be doing it. Frank will be on the hot seat next time, so he'll be presenting, and I can take the questions.
Thank you.
But yeah, thank you for coming. I'm gonna like send all of these to like Les right now. And also thank you to everyone who came. I think everyone should be gone, but yeah, Les, you can cut it like 10 minutes ago.